Hello, this is Jianshu Chen from National Cheng Kung University, Department of Materials Science and Engineering. I'm very honored to be here to present our awarded technology, the multi-level photosensing memory for visible light communication. And I would like to thank most for the financial support on this work. Visible light communication is a mobile wireless technology that uses visible light to transmit data instead of radio waves. It is regarded as the best candidate for the next generation of network communication, owing to its wide bandwidth and compatibility with solid-state lighting devices. This is the simple architecture of VLC system. The data is first transmitted from the internet to the LED light. The LED light shines at a particular frequency to send the signals to cell phone. The receivers on the cell phones shall work as the light sensor to capture the light signals. Then it needs other components to encode and store light signals, which might reduce the overall working efficiency of the devices. The cell phone camera records images via the CMOS image sensors, which are basically composed of a pixel layer and a circuit layer. Recently, Sony had developed a new type of CIS, where an additional DRAM layer is included to enhance the data storage capability. The TM image shows that the top layer contains photodiodes, the middle layer is for data storage, and the bottom part is a circuit section for logic processing of light signals. Imagine that if we can integrate the functions of photosensing and the memory in one single device, what will happen? Needless to say, the cell phone will become much thinner and lighter, and we can have much higher quality of photographs. If we convert this idea on image sensors to receivers of wireless communication, the photosensing memory will have a great potential for future VLC systems. There are a few critical characteristics of photosensing memories, such as visible light response, short programming time, and good retention. Both oxide semiconductor and organic semiconductor have been applied for photomemory. Because of high electron mobility and stability, oxide semiconductors should be more promising for the future application. In this work, zinc tin oxide is chosen as the active layer because of its high electron mobility. However, zinc tin oxide has a wide band gap, which makes it insensitive to visible light. To circumvent this difficulty, gold nanoparticles are embedded into zinc tin oxide. The localized surface plasmon resonance of gold nanoparticles can enhance the visible light absorption around the wavelength of 520 nanometer, and the electron in nanoparticle will resonate with the light to transmit into zinc tin oxide and subsequently enhance the photocurrent. Here is our device structure. This device was fabricated in form of a bottom gate and top contact thin-film transistor. According to this cross-sectional TM image, you can find that the gold nanoparticles are embedded in the zinc tin oxide film. The elemental mapping analysis reveals that the zinc tin oxide film enfolds the gold nanoparticle conformally. The absorption spectrum of gold nanoparticle show an obvious peak around 521 nanometer, indicative of the presence of LSPR effect. How does the LSPR effect influence our device? According to the finite difference time domain simulation results of zinc tin oxide without and with gold nanoparticle, it is clear that the LSPR effect induces the oscillation of electrons in the gold nanoparticle, leading to an enhanced local electric field intensity at the gold nanoparticle zinc tin oxide interface under 520 nanometer light illumination. The photosensing performance of phototransistors is characterized under two programming processes. For program 1, the device was programmed by illuminating 520 nanometer light for 30 seconds. For program 2, the device was simultaneously gap biased at minus 40 volt during the 30-second light illumination. The device photoresponsibility is then calculated from the change in drain current before and after programming. Apparently, the device with gold nanoparticle shows a higher responsivity, particularly for program 2, which employs a light bias co-stimulation during programming. Furthermore, 3 critical memory performances of zinc tin oxide gold nanoparticle photosensing memory are characterized. First, the device is programmed to different states using light bias co-stimulation for 5, 2, or 0.5 seconds and erased successfully in cycles. Second, using a repeating light bias programming stimulation, multi-level current states can be obtained for the device with gold nanoparticles, while it is not possible for the device without gold nanoparticles. Finally, the device with gold nanoparticles shows excellent retention over 4,000 seconds for programming with visible light wavelengths of 405, 520, and 635 nanometer. On the contrary, the device without gold nanoparticles shows poor retention. The key for the photomemory performance is the co-active layer comprised of oxide semiconductor and the gold nanoparticles, as well as the light bias co-stimulation. Under light illumination, the LSPR effect promotes electrons in gold nanoparticle to higher energy state and ionize oxygen vacancies in zinc tin oxide. Once applying a negative gap bias, the charged oxygen vacancies will accumulate at the zinc tin oxide gold interface and induce the electron in gold nanoparticles to turn on into zinc tin oxide, resulting in an enhanced photocurrent, and the electrons transferred from the gold nanoparticles to zinc tin oxide, either via LSPR or tunneling effect, will retain the programmed current. Therefore, the retention of zinc tin oxide gold nanoparticle photosensing memory is well maintained. In summary, our proposed technology features a novel multi-level photosensing memory, which can integrate the photosensing and the memory components for VLC into one device. It not only simplifies the production process and reduces the cost, but also accelerates the signal transmission speed, which further advances the future mobile communication technology. With that, I will conclude my presentation. Thank you for your attention.